Hello everyone. Now let's see the IUPAC nomenclature of coordination compounds. Before jumping on to the IUPAC nomenclature, let's brief a little what is actually the coordination compound. Now, coordination compound consists of a coordination pair that are represented by the bracket. Inside the bracket comes a metal followed by the ligands. Okay. Now, why these bracket compounds are called as coordination compounds? We'll see a little bit about them. Now, when we talk about metal in a coordination compound, metal should consist of a empty orbital, and the ligand should consist of a lone pair. Okay, these are the very necessary conditions to form a coordination compound and to form a coordinate bond. Now, we choose a metal that consists of a empty orbital, and we choose a ligand which have a lone pair. What will happen? The ligand will donate its lone pair into the empty orbital of a metal and a coordinate bond will be formed. And a coordinate bond will be formed. Coordinate bonds are usually represented as like this. Okay, this is known as a coordinate bond. And this is what we called as a coordination compound. So, in short, we can say whatever compound that we write inside the bracket are attached to the metal by the coordinate bond. Metal has an empty orbital and the ligand has some lone pair to donate into the empty orbital. Okay. Anything that is written outside the coordination pair is not attached to the metal inside the bracket. Anything that is written outside the bracket, outside the coordination pair, is not attached or is not linked to the metal by a coordinate bond. Hence, these are ionizable. The ligands are called as a secondary valency, and these ionizable are called as a primary valency. Now here we complete a very basic thing about what are coordination compounds. Moving on further to the actual topic that we want to cover, that is the IUPAC nomenclature. We want to see some rules before jumping on to the IUPAC nomenclature. Okay. Now IUPAC nomenclature. Some rules that needs to be followed or that needs to be known before actually writing the IUPAC nomenclature for coordination compound is, first is the order of naming ion, cation and then anion. This is a known rule in any nomenclature. Okay. For example, if we take NaCl, we name this NaCl as sodium and sodium chloride. We never say chloride and sodium. Why? Because cations are named first and then the anions come. Second, naming the coordination. The ligand naming the coordination pair, here it actually needed to be a pair. The ligand in a coordination compound, will take a same example that we have taken before. Now whenever if I want to name this coordination compound, what I'll do, I'll name the ligand first. Whenever you are writing the IUPAC nomenclature of a coordination compound, the elements that are written in the coordination pair, you write the name of a ligand first, followed by the name of a metal ion. Third, name of the ligand. Now, there are different types of ligand that can be attached to the central metal ion. That comes under anionic ligand, that is a negative, positive ligand or neutral ligand. If the ligand is negative, see that the name should end with O. The negative ligand should end in name O. These are some examples of a negative ligand. If you want to write it down or take a screenshot. Here if you see, each name is ending with O. For example, F, we write fluoro. If the ligand is Cl, we write chloro. If the ligand is Br, we write bromo, and if the ligand is NO2, nitro, nitrito, sulfato, hydroxo, nitrido, oxo, peroxo, thiocyanato, acetato, cyano, oxalato, and so on. Please take a screenshot of this. Okay. Further, The example of a positive and a neutral ligand are as follows. Okay. Now, you need to be very careful about what are the neutral ligands and positive ligands. Okay. And some few exceptions. The most frequently asked or the frequently given ligands are aqua, amine, nitrosyl, and carbonyl. So these are the neutral ligands. Okay. And as such. Further going on to the rules. Fourth one, order of naming ligand. Now, once we have identified whether our ligand is negative, positive, neutral, okay. How we are going to write if more than one ligand is present into the coordination sphere? Then write the name of the ligands in alphabetical order. Okay. Fifth one would be numerical prefixes to indicate number of ligand. Now, for example, the same example we are going to take NiNH3/4. Now, NH3 is a neutral ligand. The name of a ligand is amine. That comes into the category of a neutral ligand. Hope so you have taken the screenshot. Okay. Now, here we have 4 NH3 attached to the Ni. So, I am going to use the prefix tetra. So, the word is going to be tetraamine nickel. Tetraamine nickel. Mind that di, tri, tetra, penta, hexa are used for the monodentate ligand. Now, ma'am, what is monodentate ligand? Monodentate ligand are the ligands in which only one donor atom is present or only one donor atom forms a coordinate bond with a metal. Whereas, we use the prefixes bis, tris, tetra, quis for the bidentate, tridentate ligands. Okay. For example, Cu, ethylene diamine. Ethylene diamine is a bidentate ligand. Ethylene diamine, 3 molecules of ethylene diamine are present. Now we know one bidentate ligand forms 2 coordinate bonds with the metal ion. So hence 6 molecules of ethylene diamine will form 3 molecules of ethylene diamine will form 6 coordinate bonds. Right? Hence we use the prefix bis. Sorry, here 3 are there. So tris, ethylene diamine, copper. Okay, I'm just giving you a rough idea. Okay, we have not taken down the IUPAC nomenclature as such now. Now, sixth, ending of names. Ending of names. Now, if the central metal ion is anionic. Now, how to decide whether the central metal ion is anionic or cationic? That you decide by seeing the charge on the complex. Like for example, Ni, NH3. This is a neutral complex. There is no charge on the coordination sphere. But if there is any charge on the coordination sphere, then the complex ion will become cationic or anionic accordingly. Now, a very simple rule I'm going to tell you, or a very simple trick that I'm going to tell you how to decide whether your complex ion is positive, that is cationic, or anionic. Now, if any ionizing element is written on the left hand side, anything is written on the left hand side, then your coordination sphere becomes negatively charged. That is, your coordination sphere or your complex ion becomes anionic in nature. If anything is written on the right hand side of the coordination sphere, then your coordination sphere becomes cationic. Okay. Now come to the point 6th. If your central metal ion or your complex is anionic, the name of the central metal ion should end with ate. For example, cobaltate, ferrate, platinate, etc. If the complex ion or if the charge on the complex ion or the charge on the coordination sphere is positive or neutral, then no characteristic name is being written. For example, if nickel is there, it would be written as plain and simple nickel. Cobalt is there, no need of writing cobaltate, simple name is given for the cationic and neutral complex ion. Okay, now here the example we have taken cationic complex CO NH3/6 Cl3. Again, use the very simple trick that I have told you. Anything if written on the right hand side of the coordination sphere, your coordination sphere or complex ion will be cationic in nature. For cationic or neutral, no characteristic word is to be put. Okay, so first see what a charge your complex ion have, because based on that your metal ion will be written accordingly. Okay, so hence now after that remove the oxidation number of a cobalt. Now oxidation number, how to remove the oxidation number, I'm going to prepare a next video that I'll upload. You see that video after this. Okay, oxidation number of cobalt is +3 here. Okay, so hence after seeing what charge is there on the complex ion and after removing the oxidation number, the name written for this coordination compound is as follows: hexaamine, because name of a ligand should be written first followed by the name of a central metal ion. So hexaamine cobalt, no characteristic ending is given to the metal ion because it is cationic. Okay, cobalt 3, that is the oxidation state, chloride. Okay, another thing to remember in naming the coordination compound is always go from left hand side to the right hand side. Okay, left hand side to the right hand side. Now another example we're going to take is the anionic complex. Again, see the same trick. Anything that is written on the left hand side of the coordination sphere, then the complex ion would be negative and negative. That means the complex would be anionic, and if it is anionic, the ending of the central metal ion will be done in 8. Okay, so the name would be potassium amine pentachloride platinate, and the oxidation number of platinum is found to be 4. Okay, again name of the ligand is written first. Now again I've told you always go from left hand side to the right hand side. First potassium is there, so potassium. Then when you write the IUPAC nomenclature, when you go inside the coordination sphere, first write the name of the ligands. Okay, now there are 2 ligands are present, amine is present and chloro is present. Write the name in alphabetical order. Hence potassium amine pentachloro platinate. Platinate is used because the complex has negative, the complex is anionic in charge, platinate, and the oxidation state of the platinum. Again, anionic example we are going to take, that is Ca2FeCN6. Now again, coordination sphere, something is written on the left hand side, that means complex ion will be negative in charge. That means whatever ion that I have taken, whatever central metal ion that I have taken is going to end in 8. Okay, second step, I'm going to remove the oxidation number of a central metal ion, that is found to be +2. Now again go on writing, go from left hand side to the right hand side. First the name of calcium will come, then hexacyanoferrate 2. This is how you write the name of the coordination. IUPAC nomenclature of the coordination compound is to be written. Further, if the compound is known to be ionic, then the metal are written in their Latin name. Again, if the coordination or the coordination compound or the complex ion is found to be anionic complex, then the metal ion name is written in their Latin name. That is ferrate for iron, cuprate for copper, argentate for Ag, aurate for Au, stannate for Sn. Whereas if it is cationic and neutral, we use simple names for them, that is iron for Fe, silver for Ag, gold for Au, and copper for Cu. Further example, one such example has been given. For example, K3FeCN/6. Now again, first something is written, coordination sphere, something is given on the left hand side, that means the overall charge present on the complex ion is going to be negative. Okay, because it is negative, that means it is anionic, and anionic, the central metal ion will be written in the Latin form. Now as we know, the nomenclature would be written from left hand side to the right hand side, so write the name potassium hexacyanoferrate, and the oxidation number removed here is 3. Okay, second example, Fe, no such thing is written on the left hand side nor the right hand side, so the complex is neutral. Oxidation number of ion is found to be 0, so simply we write the name as pentacarbonyl ion. pentacarbonyl ion, and the oxidation state of ion is found to be 0. Okay, now here till here concepts are clear. 7th point, oxidation state of central metal ion. Now oxidation state of a central metal ion is written immediately after writing the metal ion, whether in a Latin name or a simple name, without any separation or without any gap. Now remember another thing, gap, or when I write this name, suppose see this here, a name is written here, gap is only given between a cationic and a anionic. Between a cationic and a anionic ligand. If there is neutral and anionic, neutral and cationic, and neutral, no gap is given between the name of such thing. A little gap is given only between a cationic ligand and a anionic ligand while writing the IUPAC nomenclature. So write this point somewhere. Okay. Okay. Again, one example we'll see CONH3 by 5 Cl Cl2. Again, applying the trick coordination. First, we'll see the complex sign is anionic, cationic, or neutral. Anything that is written on the right hand side gives the charge positive on the complex sign. Hence, our complex is found to be cationic. So, no characteristic ending is given to the metal ion. Now, the oxidation number is found to be +3. Then now start naming from left hand side to the right hand side. Now the name would be pentaamine. Write the name of ligands first, then followed by the metal. Pentaamine chloro cobalt 3, that's the oxidation state, chloride. Okay. Now 8th point comes the bridging group in bidentate ligand. Now how to name the bridging groups? Okay. For example, one such compound is given. NH2 and NO2 are called as a bridging ligands. Okay. The name that is given for the NH2 is amido and NO2 is nitro. Okay. First of all, our job is to remove the oxidation state. Now for the bridging groups, as follows, we calculate the oxidation state as amine is neutral, hence 4 multiplied by 0 because charge on the neutral amine is 0, plus X because we want to calculate the oxidation state of cobalt here. So plus X minus 1 amido, charge on NH2 is minus 1. Now again one trick, students, how to calculate the charge on NH2, NH3. Now we know in general NH3, this is ammonia, NH3, this is a neutral compound, so the charge present on ammonia is 0. One by one you start removing hydrogen. What will happen? Hydrogen will remove as H positive and one negative charge will be attained on the nitrogen. So NH2 is minus 1. Again remove one hydrogen. Another hydrogen is removed as H plus. Now two negative charges have been attained on NH. Hence NH is minus 2. Okay. If you want to remove the charge on H2SO4, see H2SO4, if you ionize it, it will remove as 2H positive and SO4 di-negative. That means the charge present on SO4 is going to be minus 2. This is how you calculate some charges if you don't know the charges. Okay. So NH2 is amido and the charge present on it is minus 1. So minus 1 for amido plus minus 1 for nitro plus X, again cobalt is there. We have to calculate the oxidation state for the cobalt, plus 0 because NH3 is neutral multiplied by 4 plus NO3. NO3 is minus 1. How NO3 is minus 1? Nitrogen 0, oxygen 1 lone pair, and because the maximum valency of nitrogen is 3, so it only forms 3 bonds. Okay. And hence there is minus 1 charge present on oxygen, and hence nitride NO3 has a minus 1 charge multiplied by 4. 4 ligands of NO3 are attached. After calculating X is equals to 3, that means the oxidation state of each cobalt is found to be 3. Now how to name the bridging ligands? To name or to identify or to specify that a complex contains a bridging ligand, we indicated by putting mu before the name in the nomenclature. Now for the given compound, we write the name as tetraamine cobalt, its oxidation state, hyphen mu hyphen. Again, while writing the name of a bridging ligands, one is amido and another is nitro, again write it in the alphabetical order. A comes first and then comes nitro. So hence mu amido, mu nitro, tetraamine cobalt 3 nitrate. This is how you write the name of the bridging complex. Another example we'll take. Now here remove the oxidation number of Fe first. Okay. HO2 is neutral. Charge present on hydroxo is -1 and -1, and sulfate is -2 as per told to you above how to calculate it. Okay. Now we'll write the IUPAC nomenclature directly. This would be tetra aqua ion. Why ion? Why not ferret? Because coordination sphere, something written on the right hand side, makes the complex ion cationic in nature. So hence simple, no characteristic name will be given, and hence we'll use simple ion for the name of a central metal ion. So again, tetra aqua ion 3, oxidation state as per removed 3, mu dihydroxo, mu representing that bridging ligand is present, dihydroxo tetra aqua ion 3 sulfate. Easy. Last point is point of attachment. Now, point of attachment NO2 or ONO. While naming or while giving the ambidentate ligand are given as per. In NO2, both nitrogen and oxygen have lone pair, so it can donate the electron either from the nitrogen or either from the oxygen. But at one time only one atom will give, so hence it is monodentate. But both the atoms are able to give the electrons or the lone pair, hence it is ambidentate. Now, whether at one time nitrogen is making a coordinate bond or oxygen is making a coordinate bond, this is clearly listed while giving the formula. Now, as per, we'll solve the questions first. Now here you can see CO example is given, CO NH3/3 NO2. When NO2 is given, you'll clearly know that the linkage of NO2 to the central metal ion is done from the nitrogen side. Second example, CONH3/5 ONO. From here you can clearly understand that the attachment to the central metal ion is done from the oxygen side. Hence they have represented it as ONO. Okay. Now name it. For C, whether the complex ion is cationic, anionic or neutral. Okay. Then another thing, calculate the oxidation state or oxidation number. Now first, accordingly we write the name triamine trinitro cobalt 3. Second example, something is written on the right hand side, hence the complex ion is the positive cationic, no characteristic ending is given. So the name would be pentaamine nitrito. NO2 is nitro, ONO is nitrito, nitrito cobalt 3 sulfate. Now overall, students, 10 problem we have taken. Practice this 10 problem, write these 10 problem, okay, two times, 3 times, and if any doubt you have, please do message me. Okay, so okay, have a very